All right, so now that we have an idea of how electrophilic aromatic substitution proceeds mechanistically, I do want to take a chance to look at the energy of this reaction before we step into specific types of electrophilic aromatic substitution. So we're going to continue to look at the general mechanism that was introduced in the previous video and is shown here at the top of this piece of paper. So remember, this is a two-step mechanism. The first step is an addition step where we're using the pi electrons of the aromatic system to make a new bond to the electrophile, right? So we're taking two molecules and we're making one molecule. So that's an addition step. And then the second step is an elimination step where we're using some base. In this case, it's the counterion to the electrophile to pluck off a proton and re-aromatize that system, right? So it's a two-step. We've seen several different two-step reactions throughout this year in organic chemistry, and the energy diagram is not going to look much different from those, so there should be no surprises, right? So we're going to start at some energy level, right, with the benzene and the electrophile. So let's just draw those in. There's benzene, and we'll just use E plus again as the electrophile, all right? And in this first step, we're making a positively charged rhenium ion intermediate, which is obviously going to be higher in energy. So we'll draw our intermediate somewhere at a higher energy state, right? And then draw in the rhenium ion intermediate. There we go. All right, and then overall, this is going to be an exergonic reaction. So in the second step, right, we're eliminating, re-aromatizing that system, and the idea is that the product is probably going to be lower in energy than the starting material. And it's not so much that the benzene itself is lower in energy than the starting material. It's really that the acid that we're making is going to be lower in energy than the electrophile that we're starting with, right? So there shouldn't be too much difference in energy between just the benzene and the substituted benzene. It really comes in the reactivity of the electrophile that we're using, right? So let's draw in our substituted product. And then the acid that's made in this reaction. Okay, so we have our three species, right? And so this kind of shows you how the thermodynamics of the reaction proceeds, right? In the first step, we're making a higher energy intermediate, and in the second step, we're forming the lower energy product. We connect these with pathway lines, right? So we're going to draw some pathway, some activation energy to get to that first step, right? And then when we draw the second step, we'll draw a lower activation energy to get to the product, right? So what this energy diagram is telling us is that this first step is, so this is 1 and 2, this first step is the rate limiting step of the reaction. Right? And that's because this is the highest activation energy, or transition state energy. Okay, and so because this is the rate limiting step, right, this is the step that's going to determine the rate or the speed of the reaction. Okay, second step, lower transition state energy, so that is not going to determine the rate of the reaction at all. Okay, it's important to note, right, so this rhenium ion intermediate here is the highest energy species in the reaction. The reason why it's higher in energy is because we're losing aromaticity, right? So the starting material is aromatic, the product is aromatic. As we make that addition, we're losing 2 of those 6 pi electrons, right? So we're creating a system that no longer has 6 pi electrons. And we're also creating a system that has an sp3 center, right? So this intermediate is non-aromatic. It is important to note, however, that even though this does not have aromaticity, right, that positive charge can be stabilized through resonance, right? So we can shift that positive charge around from this position to this position to that position, just through resonance. Right, so what I want you to do now is take an opportunity to draw out the resonance structures of that rhenium ion, just so you know how to push the arrows. It's a good review, and to make sure you still understand what resonance is, right? So take the time now, pause the video, and see if you can draw out the structures of that, the three different or three unique resonance structures of that rhenium ion intermediate. So if you took the time to pause the video and draw out the resonance structures, hopefully you're seeing that that positive charge is ending up in a specific position, only three specific positions around the ring relative to where the substitution is occurring, or relative to where that electrophile is, right? So you could see here it's in a position alpha to the electrophile. If we move it around, right, now our pi electrons are on the opposite sides of the ring, right? And our positive charge is across the ring from the electrophile, right? So the alpha, beta, gamma position, right? And then if we continue to move that around the ring, we could get that positive charge to show up in the other alpha position. All right, so this resonance is going to be important when we look at electrophilic aromatic substitution on benzene rings that already have a substituent on them. All right, but nonetheless, it's important to understand that this rhenium ion is stabilized through resonance, and the position of that positive charge is going to play a role down the line.